All right, so the final talk of the session is approximating constraint satisfaction problems on high-dimensional expanders. The work is by Vedat, Levi, Alev, Fernando, Granha, Jeronimo, and Madhur, Tulsiani, and Vedat will give the talk.
Okay. Thanks for the introduction. I'm going to talk about our work on approximating CSPs on expanding instances. I'm from University of Waterloo. Fernando is from University of Chicago, and Madhur is from TTI. Okay, so what are constraint satisfaction problems? I'm given a set of m constraints, each involving k variables. There are n such variables, and the variables take values between 0 and q minus 1. And the goal is to find an assignment that satisfies as many of the constraints as possible. And the mental image I have in the back of my head is that these constraints are really living on the hyperedges of a k-uniform hypergraph. Okay, so some simple examples. Trillion q is the problem where I'm given a bunch of linear equations modulo q, each involving 3 variables, and then the constraint hypergraph just puts a triangle for every such equation. Maximum cut that we're probably all familiar with. It's the problem where I want to find a bipartition of a graph where the number of edges going between the partition is maximized. So the constraint graph is just the graph itself. And a problem like max reset, we can also do this, where the constraints are just OR clauses, and the constraint graph just has a triangle for every one of these clauses. So what is the problem we consider? The problem we consider is the problem of approximately solving the CSPs. So I'm given a KCSP instance and an accuracy parameter, and I want to efficiently find an assignment to the set of vertices, like to the set of variables, such that I satisfy close to the optimal fraction of the constraints that is simultaneously satisfiable. So I'm going to write opt for this, and I want to satisfy opt minus epsilon fraction of this constraints. And efficiency is a theoretician's efficiency, so polynomial time, but something like n to 1 million is perfectly fine, even though nobody in their right mind would consider that efficient. But for this, this is the game. So why is this worthwhile? I will leave a very natural question to ask is, okay, how the hard instances of CSPs look like? And if you have an algorithm, that gives you an idea of how they don't look like. So this is useful. Especially in designing PCPs, which can be taught as very hard instances of CSPs. If you know what easy instances look like, this gives you an edge in designing PCPs. And in coding theory, you can use K-XOR as a distance amplification gadget. So if you can solve K-XOR, this gives you, an algorithm to decode your boosted code. Okay. So here's an incomplete selection of previous work. We know that 2 CSPs are easy when they're dense. Subsequent work shows that this is also the case for dense K CSPs for K larger than 2. And for expanding instances, or even something weaker than expansion, like say expanderish instances, this is known to be true by the work of Barakar, Gwander, and Storer, and Gruswam-Sinop. So the question we ask is this? Okay, so we've seen that, For dense instances, it's easy for 2 CSPs, it's easy for K CSPs. Okay, what about expanding instances? Are they easy for K larger than 2? And we give an affirmative answer to this question when the expansion is strong enough. Okay, so let me just jog your memory in expansion. So if I have a graph, I'm going to quantify the expansion of the graph by the second eigenvalue of its normalized adjacency matrix. So if it's very small, or say it's a gamma, I'm going to call it a gamma spectral expander, one-sided. And by the famous Alon-Milman-Shiger inequality, this tells you that if you have a one-sided spectral expander, the cut structure of it is going to resemble that of a dense graph. Right? Then I can also quantify expansion by the second singular value. And then expander mixing lemma is going to tell you that the cut structure of your graph is going to look like a pseudo-random graph, or rather a random graph. Okay. So what about expansion for hypergraphs? Multiple definitions. The definition we're going to consider is proposed by Dinner and Kaufman. So for simplicity, I'm just going to introduce everything for k equals 3. Okay, so I'm given a 3 uniform hypergraph. I want this graph to be locally expanding. So for every vertex x in the vertex set, I'm going to build a graph gx. And this gx is going to have an edge yz whenever there's a triangle xyz in the hypergraph. So here's a picture. The red edges are the edges yz for the triangles. And the global graph you get is the red graph on the right-hand side. Okay, I also need this graph to be globally expanding. What does this mean? For every triangle, I'm going to get 3 edges just by considering a triangle as a set of 3 edges. And I'm going to add them to my graph, and I want the resulting graph to be a 2-sided expander. Okay, so for both notions of expansion here, I want 2-sided expansion. So what we show in our work is that if you have a KCSP instance, which is sufficiently expanding, then we can compute a good enough assignment for this instance in polynomial time. So this is very vague. Let me just give you the scary parameters. So if you just stare at it a little, you see that it blows up with epsilon going to 0 and k and q, rising. But let me just assert to you that, if you consider something like 3-sat, where k is 3 and q is 2, this is actually not that bad. In fact, what we get is syntactically very similar to the result of Baraka-Gavendra and Steurer that does the same thing for 2 CSPs. So Baraka-Gavendra and Steurer show that you just solve a simple semi-definite programming relaxation for the 2 CSP. And then if the instance was sufficiently expanding, then you can find a very good assignment in polynomial time. Okay, so this similarity is not coincidental. We built on their work, and we essentially extend their work on all expanding KCSPs. Okay, so let me just remind you how BRS works. So they solve an STP, and instead of looking at the vectors, they consider, I think it's far more natural to look at the STP as producing a collection of random variables. So these random variables are correlated, and they may not have a joint distribution, right? So there might be no distribution that you can sample from that will be consistent with the, with the individual things you get. But if you look at any subset of these variables containing at most t of them, there is going to be a joint distribution that we can sample from. Okay? So t is just going to be some parameter that will, essentially quantify the complexity of the STP I'm solving. Okay. So on top of this, I want to satisfy some PSTNS property because semi-definite programming, and some consistency property that essentially just says, if you look at the distributions on some sets S and T, each involving at most T variables, if you marginalize both distributions on something in their intersection, the distributions you get are going to be consistent. So this is more or less what you would expect intuitively, but still needs to be stated. And further, I want that if I sample from the joint distribution of yj for an edge ij, I want this to do a very good job of satisfying the constraints. Okay, so let me just write it explicitly. If you take an expectation over ij, and over that expectation, if you sample some assignment to the edge yij, you're going to satisfy almost the optimal fraction of the you're going to satisfy more than the optimal fraction of the constraints. Okay, so this doesn't readily give you an algorithm because there is no way to sample from the distribution y1 to yn because there is no distribution that is consistent with that. But what we want to do now is essentially to make this distribution essentially something we can sample from using independent sampling. So I want to modify this distribution a little. Okay, so this is what Baraka-Gavendra and Steurer do. They sample an independence. They sample some sets with order t variables, and then they sample an assignment to the set, and then they condition all the variables on this assignment. And then they show if G is a strong enough one-sided expander, over the edges of G, I'm going to have little correlations. Okay, so this joint distribution of ij is going to be very close to the distributions of ij where I sample the I and j independently. So this is useful because the quantity on the right is something that I can sample with by just sampling from every yi prime. Okay? So since the statistical difference between both quantities are small, and I know that samples from yi, yij, so do a good job of satisfying the constraints, this line of argument tells you that if you were to sample independently from this distribution's yi, you're going to do a good job of satisfying the constraints. Okay, so this is a toy picture of what BRS do. So what we want to do, and I'm just going to illustrate it for k equals 3, we want to use the same idea. So we want to sample a set and then sample an assignment and then condition on that assignment. And then we want to show that when we do that, we're going to break all the correlations along the triangles of the hypergraph. So independent sampling, independent rounding, or rather, is still going to work. Okay. So, okay, this is, like, it might not be obvious how to attack at this. So I'm just going to look at a single term. And this is a simple exercise in probability theory, but it's just essentially just triangle inequality. I'm saying if I have a triangle and if I want to split it into 3 singletons, I can first split the triangle into a singleton and an edge, and then I can split the edge into 2 singletons. And then the statistical difference between the triangle and 3 singletons is going to be the sum of those 2 statistical differences. Okay, so I want to symmetrize and I want to take an average over the triangles. So as term 2 is easier to analyze, right? So you can think of it as the statistical difference over some edge jk. And this edge jk is considered precisely because ijk is a triangle in the original graph. So you can say this edge jk is an edge of the global graph. Okay, and this global graph is expanding. So if you take an average after a little symmetrizing, the contribution of that term is going to be just an average over the edges of the global graph. And by the argument of BRS, this is going to be small. Okay? So I need the assumption of BRS, and I need the assumption of high-dimensional expansion to argue that the resulting graph is going to be an expander graph. Okay. So what about the other term? So I have a triangle, and I'm splitting it into a singleton and an edge. So now I consider the following graph. Okay, it's a bipartite graph. On the left-hand side, I'm going to have the vertices, and on the right-hand side, I'm going to have the edges. And I'm going to put an edge between a vertex and an edge when they form a triangle. Okay, so this graph I'm going to call the swap graph of H. And what we show in our work is that this graph expands. So this is useful because you can, after you symmetrize and take an average, the contribution of this term is just going to be a contribution over the edges of the swap graph. Okay, so if the swap graph is expanding, you're going to see that by the argument of BRS, you're essentially done. So let me just summarize. Let's put everything together. So I have this quantity that I want to bound. I use triangle inequality. I got these 2 terms. The first term is going to be small by the assumption on the expansion of the swap graph and high-dimensional expansion. And the second term is going to be small by the high-dimensional expansion property and BRS. So if you just do independent rounding, you're going to satisfy a good amount of the constraints. Okay, so here's something that we show that is more general than this toy picture. And by the way, this expansion of the swap graph is the only reason why our argument works. Like, that's the only non-trivial thing I told you. So this is the more general version of that. So I'm going to consider this following graph. Again, I have a hypergraph H, K uniform, on n vertices. So on the left-hand side, I'm going to put subsets of n of size p. On the right-hand side, I'm going to put subsets of n of size q. And I'm going to put an edge between 2 of these subsets when they're disjoint and when their union is contained in a hyperedge. Okay, so this is the general swap graph, I guess. And what we show is that this graph is expanding. I just want to say a little something about the proof idea because I think it's really nice. So there is this idea that when we're thinking about expanders, the picture we have in the back of our heads is that an expander is just a sparse complete graph. So the intuition we use to prove this is very similar. We liken a high-dimensional expander to the complete, like essentially the analog of the complete graph. So this is what you call Johnson scheme, Boolean slice, complete complex. Like the name you call it by depends on your background. But what we show is that if you consider certain random walks over high-dimensional expanders, they mimic the analogous random walks over Johnson scheme. And these random walks are known to be expanding. So we can make this more precise by using the machinery of Dickstein, Dinur, Filmus, and Harsha. Yeah. Again, for our purposes, this is all the expansion we need. And high-dimensional expansion is actually something much stronger than this. So it's like overkill. So we can define an analogous concept for all collections. OK. These swap graphs are not studied by us and us alone. In independent work, Dickstein and Dinur also studied this. And they gave some applications in agreement testing. In fact, the parameters they gave for expansion are somewhat better than ours, but we show some other stuff that they cannot be recovered by that analysis. But their analysis already implies an improvement of our algorithm on time, so that's nice. So the expansion of the swap graphs is a weaker property than high-dimensional expansion. Some very natural collections like expander graphs also satisfy this property. In fact, the expansion we get there is like much better. And in recent work with like the same three of us, alongside with Dylan Quintana and Shashank Srivastava, we show that our algorithm implies the list decodability of certain codes built in a very natural way, where I'll just start with linear code first on, I guess, n bits. And then I boost the distance of this code just by taking XORs over the hyperedges of a hypergraph that is satisfying this property of the expansion of the swap graph. And then I can use my algorithm and some other SOS tricks to decode this code. OK, so this was all that I had. Thank you for your attention.
Questions? All right, let's thank the speaker again.